François?
Okay. Thank you very much, Pablo. It's an honor to be here, and I'm very sorry not to be able to be in person. I'd love to, but constraints can't be. I couldn't make it. I would like to start saying a few words on interactions with my interactions started actually a long time ago, and in France, and we actually had the same master, and so as we discovered, this master was and we had excellent environment in probability theory in France in the late 70s, and so at that time, I think when we talked, we realized that it was, we never met actually, but we were part of the same reading groups and the same activities with Active, and it was very interesting to discover that when we had an exchange. Okay, so the second phase, and it's very much linked to the topic of classes here, because thanks to a colleague in university what I did, I got interested in the Galves academics like 4 years ago, and it's only after that the Galves in question was the person I had heard about through Active, and then we got in touch and had very interesting discussions on lots of questions, technical questions, particularly when there was this workshop in the Institute Margaret. And so it's interesting to see that even persons you did not meet, but were part of the same school, share the same aesthetic and go on potential direct interactions. So it was in the late 70s, the early 80s, right? And it's only about 2017 or 18 that I started really interacting with on problems which I discovered in extremely interesting to me, and so it's a lot. So thank you very much for the invitation. Okay, so after this, I would like now to share my screen and actually start the lecture. Okay, so share screen. Okay. Okay, we should be able to see my screen pretty soon. Okay. Good. Can you see my screen?
Yeah.
Can you see my slide?
Yes.
Okay, very good.
But François, there is a problem.
Yes.
You have a small square with our picture there, down there.
Okay, so.
Yes, fine.
Okay. Okay, so after discussing with the organizers, I mean, I decided not to discuss what I mentioned, I mean, the work of it's, and so to focus on work which may have some connections, I will explain that perhaps in one example, on the unimodular network. So, and this will be a survey of joint work with Leonid, who is now back to Tehran, Sergey, who is a PhD student, Ali, who is also in Paris now, and James was a PhD student when I was in UT Austin, the math student, and we part of the examples I will describe with James and with Sergey. Okay, so okay, so it's meant to be in three parts. The first part, I mean, will probably be superfluous for people who are fluent in unimodular space, discrete spaces or graphs. So I think it's important to go through this definition so that just to understand the key second part, which is what we call the classification theorem for point sheet. And okay, so that's what I want to reach, and so that will be the first two essential parts. And this is this classification directly to the model. So that will be the main. And so it will be an occasion to go through a few results, which I think are important. The maker's theorem for when the point unimodular point carrier lemma, which are really the basis of this classification. That's will be sort of the basic element, and then I go to double trees. I want to illustrate this classification of linear trees by showing you some results of the double tree. So double trees are notion we introduced with Leonid and James some years ago, and that we go on developing with Sergey, and it's linked to the doubling coupling of Markov chain. To anybody who works in Markov chain, and I will show the connection between the positive and negative. Okay, and so the thing was there might be some connections with the dynamics. So this thing, of course, I will make some give some results on measure of this Markov dynamics and the connection is perfect. Okay, very good. So please feel free at any time to interrupt and ask questions. Sound seems to be okay on both sides, so you may just ask about just without the chat. Oh, okay. So I will first describe. Actually, there is a global notion which is that of unimodular discrete spaces, which are metric spaces, random metric spaces, which have special cases of point processes or can make it a bit more general. I will describe equivalent processes. Describe this point reference lemma, and then the dynamics of these objects, which we call point shifts or vertex shifts, and I will give examples, and then give the two results you think are useful. Baker's theorem is beautiful, and then the classification theorem, which we explained and illustrated in the tree. Okay. So, unimodular discrete spaces, you take a discrete metric space, and you associate a root, what we speak of pointy spaces in discrete space, right? Theology, right? And so the assumption fundamentally is that every ball takes a finite element from the definite. And interestingly, when thanks to the rules, you can get this. You can make this a Polish space, a good Polish space, and the discrete spaces may then be made random. So it's not by the equivalence class by the isometries by the D0 in bold equivalence class for isometries of this class. And so such a random is it's a random matrix space that can be in the pure space is a graph distance, or point process, you have special instances, and you say that this if what would happen on the finite set speak your inert on the bottom, then you would have that some sort of simple linear would sum up the distinct what you say is that space is equal to the propagation function P that and so
Francois, the connection is very bad. We cannot hear this.
Is the mass transport from the origin is that
Okay.
connection is bad.
Yes.
It's the sound. What? Is it the sound which is bad? Hello?
Yes, but not only. It's unstable.
Is the sound?
No, the sound is bad. Yes. No, now it's everything.
So one option would be that I send the slides and then I just have the voice without the video.
Yes.
Shall I try that?
Okay.
What do you recommend? That I send the slides and cut the video and just have the voice?
I canceled our video. Let's see if it works better.
Okay, you try something on the side?
Let's try this way. Let's see.
Which way?
Now, like it is now, because I canceled our video.
Okay. Is it better now?
It is better, yes.
Shall I go on?
Yes, let's try it. Yes.
Okay. Okay, so please stop me, and otherwise I can cut my video and send it to the slide. to broadcast the slides, to show the slides. It's not the option. Okay, let me go on. And tell me if it's bad. Okay, yeah, and so the interpretation, as I said, is that you send mass, the total mass that you send from the origin to all nodes, all points in the metric space, is equal in mean to the total mass that all points send to the origin, and you send mass in an equivalent way. Namely, you send mass based on the equivalence class of the space D, O, and V. So this is the mass transformation.
And G is a function. G
is a function which acts on the equivalence classes of rooted spaces. Namely, if two rooted spaces are isometric, then when you root them at O and V, then you should send the same mass from O to V. I will explain that a bit in more detail. And so this is the and you will see what instances of this. So of course, if the space is finite, you would condition on the side, and this would just would be the interchange of summation, because O being uniformly chosen in the finite set, it's a double sum, right? So there will be a first sum on W, which is the representative of O in D, and you swap the thing, the W and the V, the sum, then you will find this. So as we shall see, I mean, all finite spaces properly handled are modular, and the theory is meant for infinite spaces. Okay, and I will give us many examples, right? Okay, examples indeed. So Cayley graph, discrete spaces of R Cayley, the irregular graph or various grids are unimodular discrete spaces. There are random discrete subsets of RD or RK, like point processes, stationary point processes, are when equipped with sufficient distance, are unimodular. Various graphs will explain the eternal delta tree in a few seconds. Is unimodular. If you look at the graph of the walk, it is also unimodular, and seen as a subset of, say, here R2. And so the key object is the conversion of the stationary point in any dimension. If you build any equivalent graph, maybe you start putting edges between points in an equivalent way. So here, for instance, that this the simplest situation would be that you look at what is called the universal map point, which is the environment of the point, and in function of this environment, you decide whether you go net from this point to this or that net, right? And so all these graphs that you build in a Euclidean tree, which are equivalent graphs on the stationary point process. And it was, I think it was understood very early by the Jacques Neveu, for instance, are unimodular under the conversion. Okay, so that's so it shows that you have class objects already. The image of the stochastic process with stationary increments. So you take yn to be a stationary stochastic process, say with values in RD, and you go forward with the increments y and backward with the minus y increment. So and so the map which build therefore the x form a subset of RD, and the map that leads from the Y, the image on RD, which is the trajectory of the process with stationary complement, is a measurable from RD to the Z into T star, which is the space of rooted metric spaces, and therefore D rooted at 0 is the random state space, which will be used throughout. Okay, so you need, of course, certain assumptions. So the transients here, accumulation, and simplicity assumption. So as to get no accumulation. Okay, by the same argument. And what is the graph? This is you have your point I, and value of the stochastic process xi at time I with increment yk, which are stationary. So this graph, it's a thin subset of RT. It is not in any sense a stationary point process in RT, but nevertheless properly rooted 0. This object is unimodular. Okay. Very important thing that we'll use later is that it's a concept introduced by Thompson, point stationarity. So point process is point stationary if its point distribution is the space of measure with no accumulation, and we satisfies one of two important. These are the mass transport equation for all translation invariant G, or P is invariant by all bijective point G. And I will explain what the point G is. And so it generalizes the notion of point stationary, generalizes the notion of stationarity. A very good example, which is point stationary but not stationary, is point process. Right? So you're under the pan, and for instance, think even on R, and you have a remote process. And this remote process has no mean. So the random variable yi are the interval times of the process are iid, but they are finite at no first point. And then under the pan of this point process, you can show very easily that this very thin point process R is unimodular under its pan measure. There is no stationary measure. Okay, so it shows this of infinite object, and of course, as I announced, it's very important result. The local limit of any finite point exists, and you pick this graph. You should note this graph as one of the finite limit of those random. Then the limit, when it exists, the limit is okay. So now what are equivalent processes? These like thinning in point process theory. So first we will introduce the notion of marking. The marking, like in point process theory, is a function t equals d to some space, a measure of space, and an equivalent process is a map that assigns to every d a random marking, which should be ZD, which should be compatible with isomorphism. If two spaces D1 and D2 are asymmetric, then the mark, which is a way to associate this set of external objects to the all points of the space should have the same distribution, plus a measurability condition, which I spell out mostly interesting equivalent processes would be processes which are deterministic, which are the functionals of the point process, factors of the point process, or factors of the space. And so for this, you need a measurement condition, which in that case would spell out that the map DO associates the fact that the triple DO with its mapping as a certain property A should be measured. Okay, we don't insist on measurability issues too much because it's a bit technical. Okay, and so the key lemma here, which is classical, is that if DO is the universal space, D is an equivalent process on D, and this equivalent process could be either deterministic or random. Then the triple DO with its mark is also unimodular. And so it's like in point process theory, when you build point processes, then mark point processes, and factor mark. It's a well-known that you can extend the point process to a mark point process. It's exactly the same thing. But it works in a much more general setting. Okay, and often so the terminology of data that mark unimodular graph. Okay, and what is the equivalent subset? Important later. It's a set of points with mark 1 inside 0, 1 value. Right, so it's the stemming. You have a space, and you pick point in a way which is equivalent, and it makes a subgraph or subspace. And the intensity is just the probabilities that the root belongs to set SD, which is the set of points with that mark. Okay, very good. So let me give a few results which will help setting the result that we use, the classification result. The first result is a point average lemma. This terminology is due to Lovash, who got the same result as we did, and maybe this way, let's say it's the point terminology in our paper originally. And so let me phrase it in simple terms. That's not invariant, but if GO is a uninuclear network, very unmarked, and VG is infinite, vertices of G is infinite, then any covariant subset of V is either empty or infinite. So the cardinality G belongs to 0 infinity. And so people do this in point processes theory, right? So either you have an infinite number of points when it is stationary, or you cannot start somewhere. And so it's very surprising that these things work quite generally, and it has a very beautiful proof based on mass transport that essentially extends to any unimodular discrete metric space the principle of the one for one. Okay, and incidentally, there are lots of unimodular extensions of the theory of measure transformation. There is a sort of unimodular theorem, and lots of interesting things that you know, but we just want to stress this. Is the sound better now?
Yes. Yes.
Okay, very good. Okay. Excellent. So now, yeah, questions?
No, it's
No? Okay. So let's now, please. Vector shifts and point shifts are dynamics on discrete spaces, right? On discrete unimodular spaces. And so they are very different names in the picture. The terminology proposed by proposed by Torreson and so point shift and point shift for point positive. We name them vector shift for shift would be universal for discrete spaces, right? So you select, the principle is that you have the root, right? And you select one node, a point of x, in the discrete root structure, and as a function of discrete root structure in an equivalent. So if two points are at the same environment, right? They see the same graph, then they should be mapped to the same image, I mean, up to isomorphism. So, and the principle is that you select a node in this way and you move here. This is the point. I think the concept is known as a master poetry is due to Maker, with name mass personality. Tourism uses terminology and a lot of things name them application. And so, what is it? For point of this, point shift terminology. What you do? You have a measurable function for the support of a point process itself, right? Which maps a point to another. And the thing should be translation invariant here. The translation invariant point shift is such that when you translate the images, you translate the whole point, the edges to the image points are not affected. So the images are translated with the shift, right? And so another way to get it, you see it on the right, is that you pay, if you want to learn what the image of x here, you can bring it to 0. Useful, right? You bring it to 0, then you apply g in 0, right? The g is called the point map. You see where you are shifted, and then you shift back the whole point process. The initial shift was in the notation, and you shift it back to time 6, and you get the point which is. So you can always put the image of the point after having brought this point to the origin, and then you bring the whole thing back to origin. Right? So that's what the point shifting is. And so the point fish, which was very important to us, is the Ferrari and Torreston point shift, which is called the point stick point shift. Right? So you are under the arm of the process. Here you make a strip to the right in R2, and in this strip you look at the first point, which is right, and you jump. And you iterate this principle. If you want to learn how the trajectory goes, you bring back the image point that you see on the right and the top figure to the origin, and you iterate the principle of having a strip which is centered at the point and choosing the next point in the right. With Charles Bordenave, we studied another one, which is in the spanning tree, which is called directional point shift. So you plane, you want to go east of like and his colleagues, and you look at the closest point, which is eastward, and progress there, and then it. Right? So it's a locally defined navigation route on the support. And so, and you can extend that to, you can define the covariance vertex shift, which is the same principle on the discrete metric space problem. So, what is a covariant vertex shift? It's a map from the set of vertices of the graph to the set, which is preserved by a network isomorphism and you change it, right? So it's can be extended into metric spaces, but it's exactly the same principle, with the translation being replaced by okay. And so here is a good illustration of the fact that this universal world can be seen as an extension of the classical world on the Euclidean spaces. There was this Maker theorem, which says that in measure preserving point shifts are those which are bijective and only those, right? And so you have the same result in any unimodular space. If F is a vertex shift on the unimodular network, then theta F preserves the distribution of this randometric space of R if you want, if and only if FG are seen as a map from the set of vertices to itself is a posteriori measure. Okay, now I come to what I want to pitch, which is the notion of vertex objective graph. And see here I give illustration which comes from the I think that's the Pablo's big point shift. So you've seen how you move from one point and select the next. It's a navigation. You see islands in both next islands. But now you think of that globally and you apply the same thing to every point in the point process. And what you get is a graph, which we call the F graph. The F is the point shift, right? And the F graph is the set of all connections made by this navigation. So it's a set of so the set of is the set P of the graph, and the edges are all edges V and V when V varies on the set of vertices. This is and so in the Euclidean sense, very clear. This is union of all orbits, something from all V. If you see F as dimensions, right? And so an important object the classification is the stable manifold the foliation of shift, which is the exact analog of the stable manifold whose dynamics, the Fourier partition of the set of points of the Euler space is defined by the equivalence relation that two points x and y are F equivalent if and only if there exists an integer n, non-negative, such that the orbit of n of x and the orbit of order n of y meet EI. And so this equivalence relation defines equivalence classes which are called F for each. Okay, and so you may have the point shift equivalence classes itself, and the foliation is a refinement of the connected. Okay, and so a very important theorem is that the foil is a unimodular displacement. Very surprising and so this is I think point shift on the Poisson point process. So you see you go to the right and you go to the next point to the right, and you see in red the foil. These are points which, when you iterate the point shift an equal number of times, which is arbitrary, so you reach the same point. Right? And so to be on the foil, it may be because when you apply this one, the image, this would be like children of or children of the same. And so it's a factor of interesting object, even for simple Poisson processes, any interesting object. Okay, and now I come to the point I wanted to reach, which the proof is based on the recurrence lemma, essentially, right? It says that if F, so we start entering into the core. So if F is a covariant point shift on the universal discrete space, D is O, right? Almost surely, the component C of the origin is a unimodular discrete space that belongs to one of the three following classes. Right? So, this result is on the classification of the component containing it. So either it's of class that we call FF, this component of the origin is finite, and each of these points. And the second class, one just think, is the IF, I for infinite and F for finite. So C in that case is a two-handed directed tree, and with all if x point being fine. And the first and most elusive class, we use many examples later, C is a one-handed tree, and all its points are infinite. Okay, and let me explain it a bit in more detail. So it's on the system that we proved is near-middle that I mentioned a bit earlier. Okay, another way we don't comment on that classification theorem is what I will say is there is a good way of describing one-handedness in such a directed tree, right? So we say that connected component, so the connected component totally linear, right? That this connected component is such that it is evaporated by F if F infinity of this component is near this. Okay, so it means that for all x in C, there is some n positive such that the set of descendants of order n of x, and you remember that the parent was the image of the point by F. And so if you look backward at the descendant set, then for every point n, there is an n. For every point there is an n set of x is one. So there is no infinite lineage one point if f of x is the path of this is the definition of evaluation. And so let me now browse through the three classes. Every class is the nearest block on the BTP. So you go to the nearest point, right? And you know that in the Poisson process there are neighbor points which form loops, and there are small subtrees that lead to these loops, right? To these loops. And so this is the archetype of it. And so this is one class in this classification. T is finite, each point is finite. T has a unit cycle of some length n in the Poisson point process and for nearest neighbor 2. And the F infinity of C is the vertices of the cycle, and therefore F does not evaporate. So this is this picture. Second picture is the IF class. So IF means that now the number of nodes in the component is infinite, but the propagation is finite. So C is infinite, that's the first point. And each of the F points is finite. Okay, so in a sense, if you think of this genealogy interpretation, there is one lineage. So first, I mean, everybody lineage to Eva or Adam. It goes up to the parent of the parent of the existence, infinite, right? But if you go back, there is a lineage which goes to minus infinity. Right? There are nodes, the former backbone, and this is the other end. These two ends same, right? Therefore, each foil is a junior foil. But if you look at the number of points which are the same generation as a point on the backbone, it's always fine. So the number of your cousins, first cousins, part of the system, first cousin, second cousin, is necessarily fine. Okay, and we'll give an example later. So finite for infinite number of it can only have two ends, right? One at Eva or Adam, and the other at the anti-Eva or Adam, which is called the backbone, the triangle. Okay, and now the example. So at the complete point shift and the point shift that we introduced with Charles are in this class. The I is infinite. All these foils are infinite, and the foil order is like n. Okay, so, and in that case, C is a one-ended unimodular tree, and there is a right? So, actually, this is one way of rephrasing the fact that no point has any for all points number of descendants is fine. Okay, and that's what I want to illustrate in the example. Let me call a family tree a directed tree in which the out degree of each vector is okay. Call an eternal family tree such a directed tree in which the out degree of all vertices are exactly equal. Call a rooted FT or EFT as well. And call parent vector V the one with the outgoing edge V if the image of V is. And so I don't want this analogy. You call parent the image by the point parent here you are directed tree, right? So the image by F. And if you go backward, you get the descendants, the children, the non-children. You call Vn the set of descendants. D of X the set of X. Okay. And so, say a random family tree, define a random family tree as a random network with star. And the unimodular family tree as a random family tree that satisfies the mass. And we call it random proper in the expectation of the number of okay. So an archetype is the eternal tree, which I define by this picture. So you take the root, you hang a tree, which is a Dalton Watson tree, classical one, and then you create a backbone to infinity to Adam, Eva, what you want to name it, right? And on each point of this backbone, the point there, you create a size bias recursion journey of the Dalton tree. And you create that you see hanging at this cat here, which each of them being a Dalton Watson tree with a classical reference factor offering the distribution for each child. The progeny of this star up to the fact that the child is the size by distribution of the reference. So this is called the eternal Watson tree, and it is unimodular if the distribution is as a mean, right? Which describes which in that case is a term. Okay, so this object, unimodular eternal family trees, can be seen as a generalization of branching processes. So the proposition is that T O is the unimodular tree. If T has infinitely many vertices almost shortly, then it is eternal. In addition, TO is a proper random EFT with the expectation of the number of descendants of order n being 1 for order n, and the total progeny being always in infinity. Whereas if T is finite with positive probability, then you get that E of n is less than 1. Okay, so the subtree of descendants of the root of infinity, in that sense, is seen as some generalization of branching processes. These are this is quite broad view, but the important thing is that the unimodular EFT is always critical in the sense that the mean number of children is equal to 1. So, right. So, and so you will see a bit later. Interesting thing here, you get that the expectation of number of children of generation n for all is 1, but the expectation of the total. So in the II class, it's in a second, we get the total progeny, even though the number of lessons will be indeed, it's okay, and now what is the key point is that there is a direct connection equivalent between unimodularities and dynamics from unimodularities. This says, okay, let me phrase it. Let GO be a unimodular network. Let F be a vertex sheaf. Then the component of the F graph containing, let's call it CGO, component of the F graph GF containing O, then this object, condition on infinity, is a unimodular. So let me phrase it in words, right? Think of any of the objects that we have and any discrete metric space on which you define an navigation. Okay, so if this navigation rule as component, look at the component of the head graph, this navigation, right? Like the trees I've seen for the package tree or tree with char, okay. Then this tree is a directory tree because there is and this tree is a unique EFT. So it's always critical in the sense that the expected number of lessons of any order is less than 1, and therefore it will satisfy the classification theory. Right? So, in other words, as any dynamics that you may dream of on any unimodular space will create the tree of orbit being in one of the 3 classes of it. Okay, this is the statement I want to stress because it's surprising, and we see, I mean, so we is investigating lots of examples to explain one example simulation, so for instance, we know that in a sense that it was already known by three-point shift, that this three-point shift is of the II class, the population, but we knew that the sub-trees were infinite, right? However, we also use that to number the points of the personal point process, right, to find the enumeration, which is measured. Okay, but the point is that this classification will be true for all dynamics that you may bring. You may define provided these dynamics are measured, equivalent, and bear an object which is okay, and I want to illustrate that now on the W. So, but is my clear at this stage? So they go.
Why do you need the criticality?
No, I don't want criticality. Criticality is the. I will think about it, right? You have one parent. Send around to your parent. So your children send you mass 1. The mass out is 1, emotionally. What is mean mass in? 1 by mass transport. So you mean about children. And so if you have
I think it interrupted and the Zoom was not. No, so we had
trees typically must be an EFT which is critical, right? So critical is the concept. But here it is very important that the criticality, especially in the II class, right? Because you know that the total number of descendants is finite, but nevertheless, that will be heritage because you know that the mean number must be infinite. By Fubini argument, right? You have in mean one the number of children which is one, the number of grandchildren which is one, number of grandchildren which is one, and you know that the sum of all these things is infinite. But nevertheless, you know that in the IA class, maybe for instance in the tree of Pablo, Pablo is involved, but they should name it differently. In the split point shift, the mean number of descendants, of course, is one, it's equal, but the total number of descendants, mean number of children is one, total number of descendants is finite, but mean infinite. So there are factors everywhere. And it's insist on that, it's a question, because it led us to study the unimodular Minkowski and the unimodular Hausdorff dimension of all these objects. Right? So we introduced the concept based on the mass transport to analyze all these factors. So we will discuss that. But it's very essential here. If you marry this observation of criticality, which is here, and the which is emblematic of many problems, you necessarily, in these objects, find factors. Many factors in heritage distributions and quite non-standard objects compared to what you would expect by introducing just a dynamic on the universe. Did I answer the question?
Yes. Yes.
Okay. Any other question before I move to the application?
It doesn't seem. No. No.
No, I wonder. Okay, you may ask questions later on, right? Okay, and so our support has been, so we have been doing several things on this unimodular dimensions. But what we do now is that we look at many objects of nature and try to put them in this framework to see what we have. Right? Here I will describe the doubling. I will describe the doubling graph of the chain, of the market chain, and I will discuss the positive and negative case, and I will give measure value the extension, and treatment is perfect sample, which is something important. Many problems, including in host processes and in dynamics, neural networks. Okay. Right. So here's the pathwise representation of changes in very classical. So you have the kernel XY. So it will be a discrete space, the state space, and you get this type of pathwise chain that you represent it as t plus 1 is h of xt and eta t. Eta t is a source of randomness that depends on x, right? And so there is one, as you see, when you are at x, you call eta t of x. You apply the function a of x and eta t of x, and you tune things in such a way that p, the property that h of x, eta t of x is 1, is p of x. Here you choose the eta in such a way. So it's a pathwise representation of the market chain. And okay, you can do that throughout and get what we call the doubling graph of the market chain, right? Not sure this term is reformed, is universal. Everybody has seen graphs of this. Okay, and the coupling from the first algorithm is essentially the application use of this type of graph, where you fundamentally look at the dynamics of this type, and intrinsically, when you reach a point, you apply the thing at the next point. So when two trajectories meet, then they merge. Right? Sort of the essence of the doubling coupling, and it is used for perfect simulations. You know, in the finite. And you go backward in time, look at all trajectories starting from all points, and until this trajectory is met, this is a this. Okay, in the case where the etas are higher in time. Right? Okay, so the interesting setting, so this theory is made for finite spaces, and there is very little discussion on infinite space, okay, there is some work, but Sergei sharply paper infinite space with sufficient condition for uniform coupling, but so here the state space is infinite countable. Transition matrix is reducible apparently. So that could be a positive for transitions. And we introduce an object which we call the bridge graph. The bridge graph of P is the subgraph of the double graph. Vertices in the union of the path starting from all points. There is a reference point in space that we call O, X star later on, and you look at the union of all trajectories starting from O, all times. And this is the bridge graph of the bridge. And so this is the graph that will happen for what we will later on call the renewal approach, where you put the point jump up of an integer, right, which is negative, and then move down back to 0 until you reach 0 and 1. Right? And so you would get the infinite space, the double graph, which is the blue graph, and the bridge graph. Okay, and we studied this viewpoint of classification, bridge graph of positive recurrent chains with James and Naomi back in 19, and we proved that if Xn is positive recurrent, and the bridge graph is a connected it is unimodularized, of course. So there is a way to choose the root in this bridge graph, which makes it unimodular, and it is of type IF. Namely, it has a unique infinite path beta. All its intersections with here in Foyt intersection with times are almost finite because of the classification. And so, and here the global picture is the one that you see here, right? You start all these bridge graphs, right? You have all these trajectories starting from the specific point, and you in fact prove that there is a single infinite path. So to the right is one thing, but to the left is an important thing. So there is only one thing that comes from the in terms of the structure of the tree, the space of descendants has only one lineage, which is successful to minus it. Right? That's the way of looking at it in terms of genealogy. Right? And so this intersection of the infinite path with the origin is the perfect sample of which extends the theory which was made by Professor and to the infinity. And if you look at the intersection of blue infinite path with the origin, you get the specialist. Okay, and now the thing is that in the non-recurrent case that we studied is side A, if Xn is non-recurrent, then the bridge graph is not unimodular. The probability network, of course, but it has a very interesting property. It is locally unique. It's a very beautiful concept introduced by in a completely different concept. So you get an infinite graph, and there is not unimodular. So you get a subprocess by descending, and you remember what the unique is, right? I defined this function on purpose earlier. And this object which is embedded and hidden in the infinite graph. The infinite graph, there is no way to choose a root. But if you look only at the subgraph, and of course it's only interesting if the subgraph is infinite, then the subgraph is infinite. So, and Tom called that really. And this guy, in the Markov chain, in the numeric case, what you get is, you look at the expressions that start from the reference point 0 at the time t until the first bit of time is 0. And this structure is a very thin structure because the expected time to return to 0 is thin. So it is very thin. But in the same vein as the point such line produced by Hermann is a very important concept in Union theory. Here, this object also can be proved to be union. And so the whole structure is an example where I show at the same time for the renewal EFT that I described a bit earlier, the Markov chain this graph, which is in a sense hidden in the Markov chain bridge graph of the green graph of this Markov chain. This object, the red object, is union. You cannot find a root that makes the blue structure union, but the red one is union. And this allowed us to analyze. Okay, and so what we prove is that this local multimodular network, which is hidden in this return time graph, is either a forest tree, but it's either if it's a tree, it's unimodular. Otherwise, we call unimodular EFF, eternal funky forest. The fact that the component of 0 in this forest is a unimodular. And so it depends, in the renewal case, depends on the exponent of if you have Pareto distributions for renewal process, the criticality is for 1/2. For heavier than 1/2, you have a forest. For lighter than 1/2, you have a tree. Okay, so this is the proved. And the surprising thing is that in no case, I mean, be it a forest or be it a tree, the component of the origin has no between parts. It is of the item. Right. And so it's very important for what follows, right? So the whole T set intersection of the non-recurrent bit graph with time. And so, because the foliation, because using the unimodular structure which is hidden there, you can prove that this is an infinite arc. Nevertheless, so if you look at the privileges of any point which is in this T set, which is the intersection of the blue graph with the 0 time, then the predecessor, the descendant, if you want, blue graph, the set of descendant is almost surely fine. Right, and so that's okay. So let me summarize it works technical. Well, the phase transition from positive to non-recurrent in the Dublin theory is the transition from IF to and so it means that the foliation, so in the IF case, you get infinite descendancy, right? And this is where you see stationary, right? And the foils in the as soon as you move to non-recurrent, you move to the other phase transition is there. And then there is no infinite path, but the T sets become infinite. With nevertheless pre-images which are all locally for any point which are finite. And so let's summarize the thing. The phase transition from for perfect simulation from positive recurrent to non-recurrent is the phase transition from I in the classification of units. Okay, so this illustrates that these things are present in nature, although we are not used to see them this way. Right? But now let's look at how it's used. It could be used. So you can introduce very interesting objects related to Markov chain theory, which are stochastic extensions of very classical objects in the Markov chain theory, like the taboo measure or taboo and potential. So these are random objects with random point processing, which are again some modification of information. And if you look at this, there will be point processes, and their mean measure will be the classical taboo measure. Classical potential. Potential measure, of course, in the right case of infinity. But we'll see what happens. Okay, let me describe it. So it goes like this. You want now to define dynamics on random measures, right? And not on trajectory. You know that local. You cannot find a trajectory that comes to minus infinity. You cannot make a perfect sample. But you can make it for measure. And you do it like this. You define a dynamic which is called a taboo dynamic, which at a measure on S associates a measure on S. And it uses the same randomness as T. And it goes like this. So look at the equation at the bottom, right? So you will transport mass. So what is the mass at Y at n=1? You look at all those x which were in the state space different from the start. You look at the mass at x at time t. If the edge going from x to y there, then you place that and add it, right? And you add also something that comes from x star. If x star is by delta t sent to y. Right? This is for x different from for y different from x star. For x star, like in the taboo. And so it's illustrated here. You see how you extend the dynamics for which the pathwise dynamics of the thing by the dynamics of measure. When you add mass, you see in the 4, that is mass 4 and the mass 5 that come to the point and you indicate 4 to 9. And the mass is correct here. And so that's what that's the taboo dynamics for measure. With the exception of the ground state, zero, right? When you always
François,
okay.
Excuse me,
And,
could you
yes.
please return on one slide
Yes.
back?
Yes.
So what
Yeah.
do you call the previous one? The x is x star is a fixed point in S.
Yeah.
Is a fixed point
S
in
is
unit
the
side.
same.
That's a taboo.
S is a state. Yes. X star is it's like in the taboo probability. You pick when you define the environment measure of the non-recurrent Markov chain. You fix a state. You forbid that to return to the state, and you look at the taboo measure. It was 0 before start. And S is a state which is discrete and counted, which is infinite and counted.
Okay, thank you.
Right. Okay. And so this is exactly the same picture as in the first slide for the thing, but you see this dynamics, right? Okay. But now with this modification, which is a taboo modification. And so what is now introduce the notion. So the T set is an infinite random set, which is the intersection of the bit graph with time 0, and you can prove by the IINS of the underlying structure that finitely many type zero privileges, right? That's the key reason, right? And that's really the statement of being high. Easy to prove that it's high in the classification. And called taboo multiplicity of a vertex in T, the number of zero privileges without other. So it's the Ti belongs to the T set, and the multiplicity of I is 3, because there are only 3 points, which out of which you reach I without reaching 0 in between, right? So there are exclusions that start from 0, do not touch 0 and reach I. Right? This is really the taboo extension of the. And so you see the connection. It is because you build the bridge thing that only things starting from 0 matter, and you prove that the structure of return time to 0 is a unimodular graph, and it is necessary of type pi, right? And therefore, this T set and the taboo multiplicity is well defined, it's locally defined. It's fine. Multiplicity is fine. Okay. So we just define the point process, which is called the taboo point process on S, which support the T set, and this is the taboo multiplicity. Right. And the theorem is the taboo point process is a stationary solution of the time. Is here. Okay. It must come after, right? But so the key observation or result is that this. Hello?
See, we are here.
Okay. There was a thing stop.
What happened?
Oh. Okay. Anyway, I think I've not seen time. I'm very much above time, so I should stop soon. But let me not bring the slides anymore. The taboo point process has an intensity, a mean measure, which is the taboo distribution of Markov chain theory, and the same holds for what we call the potential measure. The potential measure is the same as the taboo measure, but you don't kill things at 1, at 0, star, but you restart a new thing at x star at each time. And so what we prove is that this potential point process is locally finite, is globally infinite, right? But its mean measure is infinite. So there is something very, very cute here, is that hidden in the fact that for an unrecurrent Markov chain, the potential measure is infinite, you find a finite object because of the IIS in the unimodal classification, which satisfies the taboo dynamics, so it's a decent dynamics, which is the potential dynamics, total number of instructions, right? But its mean is infinite. Okay. And so there's a lot of connection with perfect simulation. Too much to describe that. And I'm sorry, you should have very much. I apologize. So let me stop here.
Thank you. Thank you, Francois. Very nice talk. Is there any question or comment?
So, if I understood correctly, so I don't know how Pablo enumerate points for some point process, but if I understood correctly, things like perfect simulation for Markov process or systems of interacting process can be presented in this framework. Is that correct? Questions like, is this perfect simulation successful stops that can be presented in this framework? Is that correct?
Yes. Indeed, you can indeed, for the classical thing, which is the positive direction case, extend the results, initial results of Pop and Wilson to the countable infinite state space and extend the results in pretty much the same way. And in the non-recurrent case, you can prove that this taboo point process, which is a process whose mean is the taboo probability, that this guy also, at least in the monotone case, is constructible, like in the point process. The perfect sample can be simulated in a finite state space in a constructive way, and the taboo point process. So the taboo point process is the sort of analog or natural extension of the perfect sample. In the positive case, you have a perfect sample. In the non-recurrent case, there is no perfect sample, but there is a perfect sample of the taboo. The taboo point process. And this guy, you can simulate it pretty much in the same way as you can simulate when, for instance, in the monotone case, there is an algorithm with a stopping time. The stopping rule, right? Here is the perfect sample. It's local, of course, because it's an infinite point process. But if you move on the restriction of that on the compact, in the monotone case, you can simulate it, and it is constructive. And so there are random objects which are extensions of fundamental objects, which come from unimodular theory. And that's, I think, that's one way of saying it.
A question? I have a question. What about quasi-stationary distributions and its relation with taboo probabilities?
Could you repeat the question? I'm not sure to understood.
Quasi-stationary distributions and taboo probabilities. What are the relation? What is the relation?
Well, the taboo, generally speaking, for Marco chain, the taboo probability is the invariant measure, right? And the connection between the taboo point process and the taboo measure is that the taboo point process, or mean point process, or mean for intensity if you want, the mean value of the mean measure of the taboo point process is the mean, is the taboo probability.
Okay, thank you.
So in a sense, it's a way of putting your hands on a random object whose, exactly as in the classical case, the mean, so the mean measure of this point process is the taboo measure, which is the stationary, the unique invariant measure. So you build an object, a random object, which is invariant by the dynamics, right? And which is a random point process on the state space with multiplicity, and the mean measure of this point process is the stationary measure.
Okay, thank you. I will.
The invariant measure,
May I ask a question?
Yes.
So in the normal problem case, so consider the system, so you coined, you invented the name Galves not as you are the first one to use the name. So if you consider this system of interacting point process with memory of variable length, and then you ask the question to decide what was the activity of a neuron a certain time t. So you go back to the past and use last time you find a spike of this neuron. And then you are obliged to look at a certain environment of other presynaptic neurons. So you can do this, and this looks very much to the kind of description you made of the foliation. So I don't have the words correction. I did never use these words, but it looks very much the same kind of construction. So is that correct? You see, using
so you could look at indeed at you could look at the dynamics and think of, I mean, what triggers. But here, I mean, in the dynamics, I mean, it's the accumulation.
No, I don't mean
Finding point shift on that is so what you put is more in the simulation part. In the simulation part, you put so here you have the difficulty of the continuum. Here currently we don't handle the continuum. Project to do that. But the connection, I think there is this chemical construction which also has some construction from the past. Right?
yes.
And so it's why I mentioned. So the thing is that the difficulty here that I see is that in this type of dynamics, you you are fundamentally, if you look at the ones that I know best, is Thibault. I mean, you really have to look at this potential, and you don't have discrete states, right? So perhaps in the case where the discrete space, you could use that to understand the structure of the simulation of this object. But what I don't know here, I would say, even if you would restrict yourself to this class of discrete state space, I'm not sure. I mean, well, there are cases where you will find this notation, right? In your models. It's not clear that this is it's more a question of view. Things that are things are relatable when the potential increases, you want to be laid down, right, to zero. So I think environments usually should not happen. And so, but the first part, yes, it should happen.
Okay.
My first part, I mean, the things that we changed nothing initially on this, because here the state space is infinite, right? But if it is discrete, then an infinite, it is positive recurrent, therefore it is of the IF class, and therefore there is an infinite path minus infinity, which is the perfect set, out of which that's for sure.
Okay, thank you very much, Francois.
Thank you.
Thank you very much. See you next time.
Thank you. Excellent. So with the person, so I'm very glad to celebrate this big event. So, congratulations.
Okay, thank you.
Thank you.
Goodbye.
Bye. Você tem